Hi, this is Tuesday, March 2nd, 2021, Physics CP, class notes about the topic of waves. And we've already had you do this once or twice, but I guess it bears repeating that a wave is a transfer of energy through time and space. So that's the definition. A wave is a transfer of energy, by the way, but not matter, through time and space. So what we used to do in the old days is in a physical classroom, I have 3 tables set up in my classroom, and we'd have 4 students sitting per table. And we would simulate being off at a sporting event where the crowd would do the wave. And so I'd walk along the front of the tables trying to encourage you students to do it. And the first students would stand up and sit down, or raise their hands, stand up, raise their hands, sit down, and then the next student, next student, next student. So the wave goes across the room. Direction of wave speed, or if you like, wave velocity, would go across the room. But the direction that any student moves, so how do we put this? The particles move perpendicular to the direction of the wave speed. And actually, there are 2 types of waves. So the situation where they move perpendicular, these are called transverse waves. For transverse waves, I can represent them by drawing a sine curve. Okay, one of my better attempts. The midpoint of the wave would be this dashed line here. The distance, pretty much physically for mechanical wave, from the midpoint to the top of the wave, which has its own name, it's called the crest of the wave. That distance is called the amplitude of the wave. The bottom point here is called the trough of a wave. Here's another crest, another trough, and the distance from one crest to the very next crest is called the wavelength. I wrote a Greek symbol for wavelength, and it looks sort of like a squiggly upside down letter Y. This is called lambda, Lambda. It's a Greek letter, and it's the symbol that we use to represent the physical distance from one crest of a wave to the very next crest of the same wave. And it doesn't have to be strictly from crest to crest. It could be from the trough of one wave to the very next trough on this wave train. It can be from the midpoint of a wave, but not to the very next midpoint. It has to be to the next midpoint that's identical in direction. So if it's going up, then the next midpoint that's also going up. So that's wavelength as well. All of those are wavelengths. So, of course, there's some physics involved here. I believe in your CK12 homework, they're going to be talking about what does it mean to be periodic? And basically that means it repeats on a regular time interval. Now, that's separate from simple harmonic motion, which is something that you can represent, okay, can represent using sine curve. And by the way, a sine curve from mathematics is the same thing as a cosine curve from mathematics that just starts at a crest instead of at a midpoint. So yeah, you could put sine or cosine curve. So I have a ball and it bounces, bonk, goes up, bounces, bonk, 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 bonk. Okay, so here's a bouncing ball. Is this periodic? And the answer is yes. It repeats at the same interval of time in its motion. Bonk, 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 bonk. And this is for an ideal ball. In a real physics ball, it would have some modulus of elasticity, so it would diminish in amplitude and extinguish due to friction. But hey, still, it's periodic. Now, is this simple harmonic motion, which they tend to abbreviate as SHM, and sometimes they abbreviate it as SHO, where the O stands for oscillator, a simple harmonic oscillator or simple harmonic motion. So don't be surprised if you see that in college. Is this simple harmonic motion? And the answer is no, it is not. You can't represent this by a sine wave. You can't take half a sine wave and rectify it and have this thing work out correctly. It just is not really that shape. So this is an example of something that is periodic, but not harmonic. An example of something that is harmonic would be a pendulum swinging back and forth, back and forth, back and forth. Okay, so that is periodic, yes. Is it simple harmonic motion? And the answer is yes, because we can actually represent its displacement as a function of angle using a trig relationship. Oh, what is it like? So the angle as a function of time is equal to some maximum angle times, and then put in a trig function if you like the sine of uh, um, some constant times time, and then there could be a phase shift that you don't care about in this course, so forget that. But where this thing is at a different moment in time, that angle can be represented by a sine curve. Nice, huh? So this is something that is simple harmonic motion and it's periodic. Another example would actually be planets going around the sun. It goes around and around. Is it periodic? Yes. You've had to calculate the period for the planets going around the sun. Is it simple harmonic motion? Well, it is in each of two dimensions independently. So if you remember from math class, you could have a Cartesian coordinate system with an x-axis and a y-axis. The x-coordinate can be represented by the radius of the circle times, let's say, the cosine of its position as a function of time. The y-coordinate can be represented as the radius of the circle times the sine of its position as a function of time. So it turns out a circle can be represented as simple harmonic motion as it goes around and around, at least in my opinion. Now, when you read your CK12 assignment, if they ask you which one of these is simple harmonic motion, and there's only one right answer, I think you better go with the pendulum, not with the circle. But I think of both of them as being valid examples. You students will have to straighten me out in our next class and tell me, so what did CK12 teach you? Are both of these examples of simple harmonic oscillators, or is only the pendulum the example of simple harmonic oscillators? All right, well, let me torture you with more information about waves in general. So we have this Greek letter that's pronounced lambda, and it represents the wavelength for a transverse wave. And the units for it, sure enough, most of the time we should work in units of meters. There's also the high school symbol lowercase letter f, or the college symbol that looks sort of like a squiggly, slanty letter V, which is pronounced nu. It's a Greek letter. And this represents the frequency of a wave. And as you would expect, maybe you wouldn't. So the units for frequency are cycles per second. But there was a fellow who studied frequency a great deal, so we also named the units after his last name, and his last name was Hertz. So we just use HZ as an abbreviation for the unit of frequency, the Hertz. There is a relationship between frequency and period. So capital T is the period of oscillation. And of course, those units would be seconds. Now, we can give you problems where the units are, years for planets going around the sun, or minutes for something else, or seconds for pendulums. As always, throughout this course, show your work and be careful to convert the units into the appropriate units for doing calculations, because there are calculations here. Here are two equations I didn't get to with yesterday's class. One of the equations is based on the relationship between frequency and time. Time, the period, is how much time it takes for it to go through one cycle. Let's say it's a pendulum and it swings back and forth. I guess by convention I should start on the left. Forth and back, forth and back, that amount of time. Let's say it's something like, for example, a period of 2 seconds. So my question is, how frequently does it end up on the left here? So it starts here, 1,000, 2 1,000, 1 1,000, 2 1,000, 1 1,000, 2 1,000. Every 2 seconds, it has gone forward and back. Every second it goes forward, then every second it goes back. So how frequently does it end up back here? 0, 1, 2, 1, 2, 1, 2. So it shows up here once every 2 seconds. Once every 2 seconds. That's the frequency. Well, once every 2 seconds is once per 2 seconds. And so mathematically, it's always going to be the relationship between period and frequency. If the period of time is 1 second to go back and forth, 1/2, 1, 1/2, 1, 1/2, 1. Well, same time back and forth. 1/2, 1, 1/2, 1, 1/2. Tick tock, tick tock, tick tock. I'm a little fast, but how often do I tick and do I talk? Well, I tick once every second. Yeah, over here. And half a second later, I'm talking once per second over there. Tick, 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 tock, tock, tock. Okay? So the relationship is the frequency is the reciprocal of the period. And there should be some awareness. Oh, yeah, hey, the units work out that way because frequency is cycles per second, and the period is seconds. And so this one up here, you can think that's, how many cycles we've gone through, a dimensionless number. So it makes sense. The frequency is how many cycles you do per second of time. And the period is how many seconds of time it takes to complete one cycle. So pick any number. If I tell you the frequency is 18 hertz, then on my calculator, I would say, oh, please tell me, calculator, what is the reciprocal of 18? Well, I've got a convenient button for that, right? Here's where you would be using the x to the minus 1 button on your calculator. And that will give you the reciprocal of whatever number you put in. So if I put in 18 and I ask for the reciprocal of it, boop, it says it's 0.5555555. So 0.055 with a bar over the 5, meaning it goes forever. Seconds, that is the amount of time, that is the period for a frequency of 18 hertz. Now, 18 is terrible to do in your head, but some of these you can do in your head. If the frequency is 5 hertz, then the period would be 0.20 seconds, 1 divided by 5. If the frequency is 100 hertz, then the period would be 0.01 seconds. And conversely, if I told you the period was 10 seconds, then you would say, oh, the frequency is 0.10 cycles per second, or 0.10 hertz. Sorry, I wasn't making sure that my audio was clear. Okay, so there's one math relationship, and there's one more I'm going to share with you this period. And all of this is for really any waves. The second relationship is called the wave speed. V in units of meters per second. Now, this is not the speed at which students stand up and sit down when they do the wave. This is the speed at which the wave moves through space and time, off in whatever direction it's going. And by the way, don't claim that the particles move vertically. It's true in this example, the student stood up and sat down, and that's vertical motion. But what if the wave were heading through? The wave can travel in any direction. So, sure, it can go to the right, but it can also go vertically up. It can be going to the left. It could be going up or down. What's consistent is to say that the particles move perpendicular to the direction of the wave speed. Okay, not vertical, but perpendicular to whatever direction that's going. Now, this wave speed is the product, here's the physics formula, of the frequency, and I'm going to write it college style, times the wavelength. So there you see it as the product of two Greek letters. And you need to be really careful because I might give you a reference sheet that lists nu on it and V on it. And the font is so small, it's hard to tell which one is which. Okay, so if I were really kind to you, I would do this as lowercase letter f times frequency. Okay, so let's do a couple of examples. First, the easy ones. Let's say that I have a wavelength and I measure it to be 3 meters. And the frequency at which the waves are going past my nose is 2 hertz, 2 cycles per second. Okay, so I don't need to do a sketch, but let's say I'm going to do one just to make it more clear. So there's one wavelength, one complete cycle of a sine wave. That's one wavelength. And let's say that this distance here is 3 meters. In 1 second, 2 of these go by. So here's the second one. And that's supposed to be another sine wave, believe it or not. And this is another 3 meters. So in 1 second, if these two waves go by and each wave is 3 meters, beep, 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 you should be able to calculate and say, oh, okay, so 2 hertz times 3 meters is 6, meters is 6 meters per second is the speed at which this wave is going past my nose. Each wavelength is 3 meters, and 2 of them go by in each second. So that's 3 meters times 2 seconds, or 2 waves per second, is 6 meters per second of time. Of course, I don't want to keep it that simple for you, right? I want to say, well, what if the wavelength is 25 centimeters? What if the period is, oh, I don't know, let's say 2.0 seconds? Now what's the wave speed? And you say, well, gosh, Mr. Turek, I'm going to have to do some conversions here. First of all, I'm going to turn the 25 centimeters into meters because I know that 100 centimeters is equal to 1 meter by definition, infinitely precise. So 25 centimeters is a wavelength, and I guess I'm writing the wavelength first. Okay, so a wavelength of 0.25 meters. If the period is 2 seconds, then the reciprocal of that is 1/2 of a second, right? 1 divided by 2 is 1 divided by 2. That's a 1. So the frequency is 0.5 cycles per second, half a cycle per second. So I multiply this thing by 0.5 hertz. So a quarter of a meter times half a cycle per second means I'm doing 1/8 of a meter per second in English units, or 0.125 meters per second in decimal form, fractional form, decimal form. I call them English units. They're still metric units. English uses fractions, metric uses decimal, but these are both metric units. Okay, ta-da. All right, I'm going to toss in one last comment, which I think might be part of what CK12 has in your reading assignment. And of course, there's a quiz with it. Just in case you don't realize it, if I had a wall and I had a spring attached to some mass, of course, there's the spring constant, lowercase letter k. And if I compress the spring or I stretch the spring and then let go of it, the mass from, let's say I start here, the mass would, let's see, how do I do this? It would swing to the right, overshoot, and then swing to the left, overshoot, swing to the right, swing to the left, swing to the right, swing to the left. And what I'm crudely trying to show you is that it is a simple harmonic oscillator. It's simple harmonic motion. And of course, it's also periodic. So a mass vibrating or swinging back and forth on a spring is an example of simple harmonic motion. There's also something called the torsional pendulum and something called the physical pendulum. Those are all examples of simple harmonic oscillators. If you want to, you can take an AP Physics Mechanics course and learn in detail how to calculate the period, the frequency, the wave speed, the acceleration, all at different moments in time and space. I will toss in one fun fact and say when the mass is at the rest length of the spring, its speed will be a max and its acceleration will be 0. When it's at an endpoint, the speed will be 0 and the acceleration would be a max. All right, there's the end of the period. This concludes this recording.